Hey everyone. So in some of the previous sessions, we've talked about how to measure cosmic distances. We talked about the parallax measurement, where as the Earth orbits around the sun, the apparent positions of relatively nearby stars within a few thousand light years of us, a little bit further with the Gaia mission, but how relatively nearby stars, their apparent positions on the sky will appear to shift, just like looking at your finger through one eye and then switching your eye and seeing that little shift compared to background objects. We also talked kind of briefly about this other method of measuring the distances to clusters of stars, this main sequence fitting method, where if I have a cluster of stars and I measure their apparent brightness versus their spectral type, if we find that diagonal band that represents the main sequence stars, we know how luminous those different spectral types of main sequence stars are. So if I see that main sequence line, that diagonal line on this brightness versus spectral type graph, if that is at a higher brightness, well, that cluster of main sequence stars must be closer to us than if that brightness is lower. The problem is that both of these methods have limitations in how far away the object can be before this works. For the parallax measurement, if the object's more than around like 10,000 light years away, even for the Gaia mission, those parallax angles are going to be too small to measure with current technology. For this main sequence fitting method, if it's more than around 100,000 light years away, you're not going to be able to get enough light to super accurately measure the spectral type. You're not going to see the brightness. You're not going to be able to detect these lower luminosity main sequence stars. So the distances to other galaxies are too large for these methods to work. So we need some other method to measure the distances to further and further objects like other galaxies. And lo and behold, nature seems to provide a new kind of star that's going to be perfect for this kind of, for being able to measure these greater distances. These are referred to as Cepheid Variable Stars. And these are stars that actually go through pulsations in brightness. They get brighter and dimmer with a regular pattern. So over the course of a few days to sometimes weeks or over a month, these stars on the night sky will get brighter, then get dimmer, brighter, dimmer. They'll go through these pulsations. So these Cepheid variable stars go through pulsations in brightness. And these stars are actually significantly changing their size. They are definitely unstable. They're not in gravitational equilibrium. So we're going to look at some of the properties of these Cepheid variable stars and talk about why they're useful for measuring cosmic distances. So what are these variable stars? Well, if we looked at the HR diagram, they'd be in this giant part of the diagram, where there's something called the instability strip. Remember, when we were talking about the properties of stars, the main sequence stars are in gravitational equilibrium. These giants, and especially the kinds of stars that we're going to be looking at, are not in gravitational equilibrium. They're literally going through these pulsations, significantly changing their luminosity and therefore their brightness. So these are a class of unstable or dying stars. And they're also reasonably rare compared to other stars. We said that giants and supergiants account for less than 1% of all stars. But even though the percentages are pretty small, if we have a large cluster of stars, there's a pretty decent chance that one of these Cepheid variable stars will be in there. If the cluster contains, many thousands of stars, there's a decent chance that some of them, at least one or two of them, might be a Cepheid variable. One of the first of these stars that was ever detected was in the constellation Cepheid. Cepheus. And again, the idea behind them is that their brightness, if we look at their brightness as a function of time, it goes through these very characteristic shaped pulsations. It'll quickly get brighter and then gradually dim out, quickly get brighter and then gradually dim out. And this will happen with a certain period. So let's mention that. So the period is the time for one full cycle through this change in brightness. So going from bright to dim back to bright again. So the period is the time for one full cycle. Now, just for comparison, we've talked about the period before in terms of an orbital period, saying how long does a planet take to fully orbit around its host star. Period more generally is the time for any full cycle of some kind of physical process. We can talk about the cycle being an orbit of a planet around a star. In this case, we're talking about a star going through these repeating brightness pulsations, and the period being how much time does it take to go through that. So again, if we look at the brightness, notice this magnitude scale. We're not going to talk about this in too much detail. The magnitude scale is a little bit weird in that the lower the value of magnitude, the brighter the star is. It's a weird scale. We're not going to worry about that one too much. Just kind of treat this as brightness with it's very bright up here, not as bright down here. And again, we can observe these very, very high luminosity stars going through these pulsations. It gets bright, then dim, then bright again. And if I have this graph with time on the horizontal axis, I can measure what is the period of this star. So in this case, we're going from about 3 days to about 9 days for going from the brightest spot to the next brightest spot. So in this case, the period is about 6 days. If we have one of these graphs, we can measure what the period of this star is. If we're just observing it with a telescope, it's going through these pulsations. We're watching that over a certain length of time, and we can measure the period. So again, the period of this variable star is the amount of time it takes for the apparent brightness of the star to go through one full rise and fall cycle. And just as a totally unrelated kind of fun fact about this, the North Star. In poetry, the North Star is used as this sign of love because it's always in the same direction. It's a constant. So in a lot of poetry, it's used as a kind of comparison with love and it being unchanging. Polaris, the North Star, is actually one of these Cepheid variable stars. So it does go through regular pulsations and changes in brightness over the course of 3 or 4 days. So whenever I hear of this, oh, it's constant and unchanging, and I'm kind of thinking, oh, it's actually going through a 3 or 4 day cycle. So kind of using science to kill the poetry a little bit, but it's still a nice thought. So anyways, getting back towards these Cepheid variable stars. In the early 1900s, an astronomer by the name of Henrietta SwanLevitt was observing these Cepheid variable stars in the, I think the Large Magellanic Cloud, which is one of the smaller galaxies that orbits our own. And this, unfortunately, was a time when women didn't have a lot of opportunities in science. There weren't very many institutions that would even allow women to enter their programs. And in astronomy, women were very often hired as computers. Basically, there were no electronic computers at the time, and groups of women were hired to go through all of the data, to be making those measurements over the course of a night when telescopes were taking a lot of photographic plates of the sky. The next day, groups of women would go through and measure the brightness of all those stars. And Henrietta SwanLevitt was one of the astronomers who was doing this kind of a job. And she was looking specifically at these Cepheid variable stars. Earlier in the course, when we talked about stellar classification, it was also these groups of women that were making those repeated observations, finding these patterns in the spectra, and and going through and starting to classify some of these types of stars. But what Henrietta SwanLevitt observed was that the longer the period of this variable star, the higher its average luminosity. So this is a key piece of information. So longer period corresponds directly with higher luminosity. So if the period is only around 3 days, the luminosity of that star is about 1,000 times the luminosity of the sun. If the period is around 30 days, well, then the luminosity is going to be around 10,000 times the luminosity of the sun. So longer periods correspond with higher luminosities, shorter periods correspond with lower luminosities. Another thing that is extremely helpful for us is that they are all very bright overall. So they're all high luminosity. All higher than average luminosity. But again, the longer the period, the even higher their luminosity, the luminosities of these stars, which makes them very, very useful because we can observe them at greater distances. If they are more luminous, it's going to be more easy to detect these stars even at greater distances. So again, the bright Cepheid variables, they have a long period. So if it's got a period of, say, looking on this graph, 20 days, maybe a little bit shorter than that, it's going to be much more luminous than if it had a short period. So longer period, higher luminosity, shorter period, lower luminosity. Yeah, longer period, more luminous, shorter period is going to be less luminous. So let's look at this period luminosity relationship. We've got these Cepheid variable stars, and there are actually other types of variable stars as well. There are these RR Lyrae stars. There's a couple other classes of them. We're going to focus specifically on the Cepheid variable stars. And once again, the idea behind this is if I know the period of these Cepheid variable stars, thanks to the work of Henrietta SwanLevitt in, kind of developing this graph and calibrating this data, if you know the period, you can identify the average luminosity. So put that as another important point. If you can find the period, you have the luminosity. You can get the luminosity. And again, the period of these Cepheid variable stars, once we found one of these Cepheid variable stars, it's actually not too difficult to measure the period. Just watch it and see how long does it take to go through those variations in brightness. So again, we can get that average apparent brightness from just looking at the star and saying, well, it's going through these pulsations, but on average, it has a certain apparent brightness. So we can directly measure that. And let's put together some of these ideas. Let me reset my video first. So let's put some of these ideas together because we want to use this. We want to use these Cepheid variable stars as a new way of measuring distance. So if I have the average apparent brightness, I can simply look at that light curve and say, well, what is that average apparent brightness? I can also look at those pulsations, and if I time those pulsations, we can get the luminosity. So if I know the luminosity from the period of those pulsations, and if I know the apparent brightness from these light curves, I can use that information to rearrange this equation and calculate what the distance to these stars are. This is an example of what we call a standard candle. Let me write down that term. A standard candle, if there's some way, if there's some kind of object where we know its luminosity, so if we have some object where we know luminosity, if I measure the brightness, I can find distance. And that distance is the square root of the luminosity over 4 pi times the brightness. So again, these Cepheid variable stars are really close to being the perfect case of one of these standard candles, since we can relatively easily measure their pulsation period. If I just watch the thing and say, how long does it take to go through that pulsation? We can use that period luminosity relationship to figure out how luminous is this star. I can also just watch it and measure the apparent brightness. So I can use those two pieces of information to get the distance. Coupled with the fact that all of these Cepheid variable stars have a higher than average luminosity, which allows us to see them and detect them and measure them from greater and greater distances. We're able to use these Cepheid variable stars to measure distances to much, much greater values than using either this parallax method or this main sequence fitting method. So let's look at some examples. Question 1, alpha has a period, let's say we've got two stars, alpha and beta. Alpha has a period of 75 days, beta has a period of 5 days. Which star would be more luminous? Pause the video and give yourself a chance to answer that. Okay, so alpha has a period of 75 days, beta has a period of 5 days. Well, we said that the longer the period, the higher the average luminosity. So if we have a longer period, around 75 days, that's going to be a higher average luminosity than if we only had a period of 5 days and a lower luminosity. So alpha would be much more luminous. So now let's say both stars appear equally bright on the night sky, on average. Which one would be further away? Well, if we look at this distance equation, we said that alpha has the higher luminosity, but the brightness is the same. So no change in the brightness. Well, if alpha has a higher luminosity but has the same brightness, in order to have the same brightness, it must be further away to kind of match those two effects. If it's a more luminous object, then it would have to be further away from me to appear as bright to my eye. So alpha would have to be the one that's also further away in this case. So again, if you want to determine a distance with these Cepheid variables, well, first you just have to kind of scan the sky and over the course of multiple nights and try to find one of these variable stars. Then you want to measure the period of the change in apparent brightness. So how long does it take to go through these cycles? And you want to measure the average apparent brightness. If you know the period, you can figure out the luminosity. And if we know both the luminosity and the apparent brightness, we can use this equation to figure out the distance to that star. And again, this works for distances much greater than we can reach with either of our other distance measurements, the parallax measurements or the main sequence fitting. And some of these Cepheid variable stars are actually bright enough that we can see them in other galaxies. This is a Cepheid variable star called V1 in the Andromeda galaxy. And over the course of, I think, a little more than a month, it goes through these changes in brightness. So these observations, or these kinds of observations, were made by Edwin Hubble. And he was the first person to use this method to actually measure the distance to another galaxy. At the time, there was a large debate on whether these kind of fuzzy things on the sky, these fuzzy objects on the sky, whether they were an object in our own Milky Way galaxy, or whether they were, in fact, other galaxies themselves containing hundreds of billions of stars. So I just want to kind of walk through this calculation. We're not going to actually do these calculations ourselves. We're just going to use this as an example. But let's say we've got this Cepheid variable star in Andromeda and has a period of 32 days. An apparent brightness of a very small apparent brightness. Again, we're not going to do these calculations ourselves. We're just going to kind of use this as a template. Well, if it's got this period, we can approximately measure the luminosity. And for this star, it's around 16,000 times the luminosity of our sun. So if I've got the luminosity and I have the apparent brightness, we can run this equation and calculate the distance to this star, which, if you convert it to light years, is about 2.3 million light years away from us. Now, remember that our own Milky Way galaxy, the disk of the Milky Way galaxy, is only about 100,000 light years across. And this Cepheid variable star, in this kind of fuzzy object on the sky, this is at 2.3 million light years away. So this was the first kind of measurement in the 1920s that actually proved that Andromeda is, in fact, a separate galaxy and not just some kind of fuzzy object inside of our own galaxy. This is another link in what we call the cosmic distance ladder. Let me zoom in on this a little bit more so we can kind of do some compare and contrast between these methods. Basically, how we measure cosmic distances, we have this sequential set of measurement methods that are able to measure distances to greater and greater distances. For nearby stars, we have this parallax measurement. And by measuring those stars, we were able to develop the HR diagram. And once we have the data for that HR diagram, we can then use that main sequence fitting method. We identified we figured out that there are main sequence stars. We figured out how to identify them. We figured out their luminosities. And now if I see another one of those main sequence patterns, we can use that in the main sequence fitting method. If we see a cluster of stars that are all about the same distance, we can make one of these brightness versus spectral type graphs, the kind of graphs that we talked about over here, and we can determine which ones are closer and which ones are further away. Well, some of those clusters that we can use this method to measure the distance to, some of those clusters contain Cepheid variable stars. And that's how we got that luminosity versus period relationship for those Cepheid variable stars. But then we can use that to measure even further distances to, relatively nearby galaxies. We also talked in one of the previous sessions about white dwarf supernovas, saying all these white dwarf supernovas, when the white dwarf is accreting material, building up a little bit more mass, and eventually explodes, Well, if those are exploding at the same mass, they should all have the same luminosity. It's going to be another one of those standard candles. And if some of these white dwarf supernova have gone off in nearby galaxies where we can measure the distances to those galaxies, we can then calibrate, well, how luminous are white dwarf supernovas, and then use that for to measure even greater cosmic distances. So with this cosmic distance ladder, we use the nearer distance measurements to allow us to calibrate all of the techniques that we use in further distance measurements. Now, think about this for a second. Pause the video and think about this. Would there be any danger in using this kind of linked set of measurements? So pause the video for a second and think about that before we talk about this. So again, we have this linked set of methods. We use radar, in modern times, we use radar ranging to measure sizes of the solar system. If I know the size of the solar system, I can use that parallax method to measure distances to nearby stars. I use those nearby stars to get my HR diagram, to use this main sequence fitting. I use those clusters to calibrate Cepheids. I use those Cepheids to calibrate the white dwarfs. One of the problems is, if there's a mistake earlier on, those errors are going to propagate to all of the greater distance measurements. So if, say, I've miscalibrated this HR diagram, that's going to throw off my Cepheid measurements, that's going to throw off my white dwarf measurements. It kind of causes those errors to move down the chain, which is why we want to use more different kinds of distance measurements. There's other kinds of distance measurements that are out there, and also improve some of these nearby measurements. I've mentioned a couple of times this Gaia mission that is able to measure do parallax measurements for much, much larger distances. Well, that allows us to better calibrate this main sequence fitting method, which allows us to better calibrate these Cepheid variable stars, which allows us to better calibrate these white dwarf supernovas. So every time we get a new method of measuring distances or improve technology to improve some of these earlier methods, those improvements are also going to propagate all the way down the chain and allow us to increase our confidence and increase our accuracy of measuring increasingly large cosmic distances. So in some of the next sessions, we'll talk about the results of when we've looked at the distances to galaxies and some of their other properties. What are some interesting results we get by looking at some of these cosmic distances? But we'll do that in the next session.